All right. Hello, everyone. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing okay today. I am feeling like infinitely better. I am thrilled that that's over with. I'm very happy to see all of you today. I bought this video game called Stray. Has anyone heard of this before? I bought it a while ago, and the reason I bought it was because people were kind of gushing about it online. It's this game where you play a cat. Like, your character is a cat, and you're going around, and like people are talking about how their cats are like pawing at the screen, and like their ears are perking up when the little cat on the screen meows and stuff like that, and how realistic the cat is. And so that was the reason why I bought the game. And I started playing it a while ago and put it down because my life got in the way. And so I started picking it up again recently. And I don't think I'm selling the game at all here in any way, shape, or form, but never for me have I experienced this massive shift of, haha, I'm knocking stuff off tables just like cats do, to there are giant eyeballs in the wall staring at me. Yeah, I don't think I'm selling the game, but that's the way the game is. It is a lot of fun. Like, don't get me wrong, it's a lot of fun, but it's also classified as like this horror game. And I was kind of, at first, like, why? And then again, there are eyeballs in the wall staring at me right now. Yeah, let's talk about operating systems. All right, so by the end of today's lecture, this part should not surprise you. I want us to be able to do file system stuff. I'm not going to repeat myself here. I really just want to get to it today. A lot of the stuff that we started doing on Friday last week, I want to finish up with today. And then my goal is for us to be able to have some C code to work with basically binary data, but in a format that is as a file system. So we'll start to do the same kinds of things as we're doing with hexdump in C code. And then, time permitting, we're going to start taking a look at the overall structure of exFAT, and then taking a look in more detail at how exFAT works. Really specifically, this one structure called the FAT, the file allocation table. The structure is a little weird looking, but once we reveal how it works, it's really just a linked list. It's no more complicated than what a linked list is in terms of the structure of this thing. So that's our goal for today. I want to finish up with this ext2 stuff. This is, again, that link to the Git repository that I created that has the beginning stuff for what we're doing, and the instructions for how to create the file system. The documentation that we were looking at here is also linked to. So I'm going to go way up to the top of this file. This is in the last lecture's lecture notes, the link to this documentation, but I'll have this up on the screen. I'm encouraging you to follow along today with the hexdump stuff. If you want to just sit back and kick back and watch, that's also super fine. I'd really encourage you to do the C coding when we get to the C coding. Again, if for nothing else than to dust the cobwebs off, but just to get a feel for, like, how do I move around in a file? How do I read values out of this file? How do I read exactly this many bytes out of this file? What kinds of options do I have for reading things out of this file when I'm working with binary data? So I'm going to pop my terminal open here. And what I want to quickly remind us about is that the super block for this file system was located at 400 in hex. Quickly at the back, is this big enough for you? Okay, awesome, thank you. The super block is located at 400, and there was a bunch of interesting stuff that we could see here right away, including the label that we had put on this volume. And that's one of the things about hexdump with the -uppercase-C option, is that it puts the ASCII representation of stuff in this column on the side. So it makes it easier to see actual ASCII encoded things in our file systems when we're looking at it this way. The superblock is at location 400, which is 1 kilobyte into the file. And then the block size for this entire file system is 4 kilobytes. So each chunk is a 4 kilobyte chunk. The place that we got to after the super block here, the place where we were starting to look at last time, was to try and find out where we can get to files. And the way that we're trying to find out how to get to files is to begin by looking at this block group descriptor table. Again, ext2 and VSFS are super similar to each other in their overall structure. ext2 has this extra thing of these block group idea, where each block group is kind of like a tiny little file system that has allocation structure and then data blocks. And there might be many of them on the disk, but with this 200 kilobyte file system, there's one block group because there are so few blocks in this thing. So this is located at the first block that happens after the super block. And the first block that happens after the super block is at location 1000. So 1000 is the same as 4096 in decimal. 1000 in hex is 4096 in decimal. And I will bring my calculator out in some points, but for now, I'm going to be able to quickly say that each block is basically that number. So like block, this is block 1, which is block 1000, or hex offset 1000. Block 2 is hex offset 2000. Block 3 is hex offset 3000, and so on, if we're working with hex like this. There's a convenient thing with that. So in this block group descriptor table structure that we've got here, the first 8 bytes here are going to be references to the bitmaps, to the allocation structures. So the first 4 bytes here, starting at offset 0 and for 4 bytes, this is saying that this 4 bytes represents where the block bitmap is. So where's the block bitmap? Where's the allocation structure for the blocks for this? Hex dump, remember, is showing this as little endian. So the first byte that we see here is the least significant byte. Everything is kind of reversed in order. When we're working with C, we will not have to care very much. This is going to be handled for us. So we're not going to have to do like byte swapping and stuff like that to get the correct endianness for these values. But with hex dump, it's showing it in reverse order. So I'm going to quickly take a step over here to block 2. So this is where our bitmap is, and I just want to see what these actually look like. So this is at 2000. And what we see here immediately is a lot of Fs. There are some zeros. Remember that this file system has 64 blocks. When we created it, it had 64 blocks and 32 inodes. Like, it's super tiny. It's really, really tiny. 64 blocks means that this bitmap is 64 bits in size. And so it's 8 bytes. This is 8 bytes. This is our entire table here. Ones mean that it's occupied, and a 0 means that it's not occupied. So FF here is basically saying the first 8 blocks of this file system are used. Then the next 4 blocks are not used, and the next 4 blocks are used. And then what follows after that is the rest of this file system is empty. None of these data blocks are used. I'm going to go back up to 1000. So I'm going to hit G on my keyboard and then type in 1000 / and 1000 to get back to my block group descriptor table here. The second value that we see, this is the inode bitmap. It's going to look a lot like the data bitmap. It's a bitmap that represents which inodes are used and unused, except this one's only going to be 4 bytes long instead of 8 bytes long because it's 32 instead of 64. But the one that we really care about here is we're trying to find that README file. So we're trying to figure out what the contents of the root directory are so that we can figure out where the README's contents are. So we have to look at the inode table here. And this is the next 4 bytes. And what this is telling us here is that the inode table is located at block 4 in this file system. So I'm going to jump ahead here to location 4000. This is going to be 4 times 4096, but switched into hex. And at location 4000, I'm going to click on this, I'm going to click on this, and this now describes the structure of the inode table itself. The inode table here is an array of inodes, effectively. And so what we're taking a look at here right now at location 4000 is inode number 1. I said this a bunch of times last time, and I'm going to remind you again, this is a 1-based array. So this first thing that we see at location 4000 is not inode number 0. There is no inode number 0. This is inode number 1. Whenever we're thinking about inodes, we're always going to be off by 1. When we talk about exFAT, this is going to get worse, because in exFAT, it's not a 0-based array. It's not even a 1-based array. It's a 2-based array. Yeah, it's a 2-based array. I don't know why. I mean, I kind of know why, but it's annoying. It's really annoying. But we'll get there when we get there. So this one is a 1-based array. And what we can see right here is this is the first kind of part of the first inode in this thing. The first inode is a special inode, and we can see all the metadata that's here. So the first 2 bytes here are saying that the mode for this is the permissions, is all zeros. There are no permissions attached to whatever inode 1 is. The user that created it here is user 0, so that's typically assigned to the root user, the administrative user on the system. That usually means that you have to be an administrator to do anything with this file. But then we look at the next 4 bytes here, and we also see that this inode, the 1th inode, the first inode in this structure, also has a size of 0. This is a special inode. This is a special inode. This isn't even actually a file. And I'm going to scroll down in just below this table here. And I'm going to say that there's this set of well-known inodes here that represent different things. So the first inode, inode 1, is this bad blocks inode. And this is what's used to represent these parts of our hard drive that have effectively gone bad and are not usable by us anymore. The one that we really care about is this one here, the root directory inode. The root directory inode is the one that represents the data for the folder on this file system that is /. On Linux and Mac OS, the root directory of a file system is just that one single /. On Windows, this is kind of synonymous with this idea of the drive and then the colon and then the /. So C:\/ is kind of like the root directory of a Windows file system. So what we actually want to look at to begin to find that README file is this second inode in our inode table. And the second inode is the 1th inode in this inode table. It's the one that comes after the first one. So that one actually appears at location 4080 here. So 80 is 128 in hex. Remember that when we created this file system, we made all of our inodes be 128 bytes in size. And then we were told in that warning we can't have dates that are after 2038 because of that. But all of our inodes are 128 bytes in size. So I'm going to go back up to the top of this table, and now we can see a little bit more about this / directory. This is the root directory that we're looking at right now. So this has some permissions. I'm not going to spend the time to decode what these permissions are. I don't really care, but there are some permissions on this. We can see that the user ID that created this is the root user, which is normal. This is normally what we would see on a Linux system. When you look at the root directory, it's owned by the root user, the administrative user of the system. And then the last 4 bytes that we see here that I'm kind of interested in right now is the size of this thing. This is a directory. This is a directory that we're looking at right now. And what we can see with this is that the size of this is, and remember this is in little endian order, so this is saying that the size of this is 1,000. So this is the least significant, then the next least significant, then the next least significant, then the next least significant. So this is 1,000 in hex bytes in size. And I'm going to bring my calculator up here, but what we figured out, that nice little trick, is that if I do this 1,000 in hex, it is 4096 in decimal, which is the block size. So what this is saying is that the size of this directory is 4096. And remember when we did ls and we saw directories, they were all sized 4096. They're all taking up an entire block to put directory entries in. The next part that I really care about is down here. These are the direct block pointers that this inode is pointing at. The direct block pointers are starting way down here. So this is the first direct block pointer for this inode. And so what this says is that the data for this inode can be found in block 5. The first part of the data for this can be found in block 5 of my disk. So we're going to scan to block 5. There are no other direct block pointers for this. The rest of these things are zeros because it's only taking one block. So we don't need to look past and see if there are any others. But a directory could have more than one block if there were lots and lots and lots of files in it. So what we're going to do right now is I'm going to go to location 5000. So block 5 is 5 times 4096, which is in hex, it's 5000. And at location 5000, what we see is the actual contents of the root directory. There's a couple of things that I immediately see here. One is the words lost plus found, and then readme.md, which is the name of the file that we put into the file system when we initially formatted it. I'm going to scroll down a little bit in this document. And what I want to do is I want to start taking a look at the structure that we're looking at right now, which is the directory structure. And I'm actually going to skip past this linked list directory and this index directory format, and I'm going to go directly to sample directory. I find this easier to parse by looking at this example than it is to just read the table that they have for this thing. The table is good, it does describe everything in detail, but I find it easier to step through this with this kind of sample in mind. So the sample that they're showing right now is, this is the output from the directory that they're currently looking at. What does dot mean? Anyone? Yeah. What's that? The current directory. And what does dot dot mean? Somebody else? Previous directory, parent directory. Yeah. Okay, awesome. These files that start with a period, they don't usually show up when you type just ls. This is like hidden files start with a dot, and this is a leftover from, we don't want to show dot and dot dot every time, so don't show anything that starts with a dot. Then the other files here are called mbox, public HTML, and temp. These two are files, and the rest of these things are directories. That's what we have to know about that directory structure. The directory structure that we have, that we're looking at on the right side here right now, it has 4 things in it. It has dot, it has dot dot. These are in every single directory. Every directory has these 2 things on an ext file system. Then it has a directory that's called lost plus found, and then it has a file that's called readme.md. So what I want to start doing here is stepping through, using this on the left side as an example, what we're looking at on the right side. So in the very first part here, what we see is the first 4 bytes of this directory entry. I can treat this data as a directory entry because I know that this is the root directory of the file system. I'm starting with this. I'm looking at the data, and I can see that there's data in it, and I can treat these as directory entries because I'm looking at a directory. The first 4 bytes are the inode number that is being referred to by this directory entry. The inode number that is being referred to here is number 2. We are currently looking at inode number 2. That's how we got to this location, but the first entry here is the entry for dot, the current directory. So the directory entry, the very first directory entry that we're looking at here says, this is this directory. It's like a self-reference to this directory. So the first 4 bytes are that. The next 2 bytes are the size of this record, so of this directory entry. In ext2, in our ext family of file systems, the directory entries vary in size. And part of having this variable directory entry size is that we put that directly in this directory entry structure. So we have to read that value before we can start reading the rest of the values from this thing. So it says that this is a 0C in size. It's 12 bytes in size. Then after that is the name length, which is 1 byte. It's 1 byte. It's a dot, so it's 1 byte. And then after that is the type. So it's a directory. So this is the same thing as what we see here. The name is 2E. 2E is the ASCII symbol for a dot, for a period. We can't really see it in hexdump's output because it's putting a dot to say, like, I don't know how to render this, but also because it's a dot. It's rendering it as a dot because it's a dot, it's a period. Then there's some padding. These zeros here represent the padding. The next one here is another inode reference to a directory entry. So this is directory entry number 1. The inode that it's referring to is also inode 2. This is a special entry for this specific directory because ... for the root directory is a self-reference back to the root directory. So both dot and ... point to the same thing here. That's what this is ultimately saying. Points back to inode 2. The record length is 12. The name length is 2 this time. And then what we're seeing here is the ... 2E is ... That's the name of this thing that shows up in our file system. I'm going to skip past some more of this stuff. So this is the padding after that. 0B here is now this lost plus found directory entry. And what we can see with this is if we go, I think it starts here at 6C. This is LOST plus FOUND. So that's lost plus found. So that's the bytes for that name of the thing in our directory entry. And then there's a couple bytes of padding. And then this is the one that we actually want to see. This is actually the entry, the directory entry that we want to see. This is the start of it here. So 0C is the inode number for readme.md. And readme.md is starting here, README, and then .2EMD. 0C is the inode number that we actually want. So now we have to go back to our inode table. I found the directory entry that I care about. I found the name of the file that I'm looking for, and I know what inode that file name has. So I have to go back to my my inode table. So I'm going to go back to the inode table. I'm going to hit G on my keyboard, and I'm going to location 4000. This is where my inode table is. And the inode that I was looking for there is C. This is inode number 12. Inode number 12, but less 1. We're going to look 11 entries into this inode table structure. And I'm not going to calculate that. I'll let you calculate that on your own. It's 128 bytes times 11, 12 less 1. That takes us to location 4580. And this now is the inode structure for that directory entry that we were just looking at in our root directory. I'm going to pop back up here to my inode table structure. Right here, And we see there's a mode, there's a user ID, although it's not all zeros this time. 2E04 corresponds to my user account, I guess, when I was making this file in the first place. But the thing that we really care about, and I'm going to skip past all of this stuff here, is this, 0B right here. 0B is the first direct block pointer in this inode for that entry in our inode. And because it's a block pointer, I can go directly to that block. And it's block B. And just like with block 4 and 5, I could go to 4,000 and 5,000. Now I can go to block B1000 here. And block B1000 is the README file. This is the data for the README file that we put into the file system in the first place. All right, okay. I know I'm a giant nerd, but I think this is just awesome. I think this is so cool to be able to like take this blob of bits that I just made on this disk and like step through it and actually find data in it. Like I put data in this, I didn't do it, somebody else wrote the code to do it, but I'm able to figure it out. I'm able to step through all of that and find the data that's somewhere inside this thing. And being able to get that, I think is, I don't know, I think that's cool. I think that's amazing. But, I mean, it took us an hour and a half to find the contents of a file. If we had to do that every time, I can't imagine using computers. That would be painful and agonizing. So nobody actually does it that way, but it's illustrative. It shows us how to read the documentation. It shows us how to move around in this file. It shows us where to find these structures. It shows us how to take a look at the content of these structures. And it shows us kind of how to follow parts of these structures to find different locations within this file system structure. I'm going to quit hexdump now. And instead, what I want to do is I really want to take a look at ext2 and spec.c. Again, I invite you to follow along at this point. If you've got that file system in your directory right now, if you made the file system, then you should be able to write the stuff that I'm going to start writing here in just a second. I want to step through some parts of this. The first thing, and I'll make this bigger now. The first thing that I want to step through is the structure that I have here defined. The thing that I really want to point at here, as much as anything else, is the use of these types, uint32t and uint8t. These are types that are defined on my system to represent exactly 32 bits, or 8 bits, or 16 bits. When I use these type names, I'm explicitly saying this property requires 32 bits or 4 bytes. If I think that if I am told that it requires to use 8 bits, I'm going to use uint64t. If it's 2 bytes, I'm going to use uint16t. These types are coming from a header file that's called stdint.h. So if you want to use these, and rather than trying to figure out what a short or a long is on your system, I would strongly recommend that you just use this header file because it's already been figured out for you. Use this header file and use these types. I'm going to scroll down here to my main function. And what I want to do is I want to step through doing some of the stuff that we were doing here. What I'm really going to do is I'm going to do some stuff with the superblock, and then I'm going to stop. I'm not going to go through the whole exercise of like actually getting data out of this file. I think that at this point, based on what we were doing with hexdump, you should be able to start doing that. And based on what we're going to do with the superblock, you should be able to figure out how to find these values and then move around in the file with these locations. So what I've got here is I have a file descriptor that I have called with open. I've opened with open. I'm going to delete this comment, and I deleted that void fd. With all the extra warning flags that I've turned on with my compiler, I'm forbidden from having unused variables in my code. It's a compile time error to have unused variables in my code. So putting a void in front of a variable name kind of says, I know this isn't used, but I need to have it here for some reason anyway. So I've deleted it. And what I want to do now is I want to start navigating in this file. I want to get to the superblock. That's the very first thing that I want to do here. So to get to the superblock, we have to go 1024 bytes into the file. 1024 bytes into the file, remember, is the same as, this is the same as 0x400 in hexadecimal. To move around in a file, we're going to use a new function that's called lseek. Lseek will take a file descriptor, and it will cause the location of our current pointer in that file to be changed. So I'm going to say lseek the file descriptor that I'm working with, how much I want to change by. I'm going to just pop open a terminal here to the side to open up the documentation for lseek, because I always forget. I can write in here 1024 as decimal. I want to move 1024 bytes. You can also alternatively write 0x400. They're equivalent to each other. So I want to move this much into the file. And the last option that we get with lseek is called whence. This allows us to go to different places based on where we currently are right now. Seek set says, I just want to go to this location as an absolute value. And because I'm trying to go to the superblock for the first time, I'm going to use seek set here. I want to go directly to the start of the superblock in this file. Once I'm at the start of the superblock, the very first thing that's in the superblock is, and I'll bring this back in just a second. I'm going to go back to the top of this file. The very first thing in the superblock at offset 0 is the inodes count. This is the number of inodes that are currently on this volume right now. It's 4 bytes in size. So I'm going to do this in 2 ways. First is I'm going to try to read individual values from the superblock right now. So I want to read the inodes count, and I want to read the blocks count. Each of these are 4 byte values. So I'm going to declare 2 new variables. uint32t, this is a 4 byte value, uint32t, inode count, and I'm going to set that to 0 explicitly. Whenever you're working with this, and whenever I am working with this, I am initializing everything to 0. I am always initializing everything to 0. When I read bytes in over top of this, I want to make sure that whatever value is actually read in is the only thing that's there. I don't want anything else in there. So I want to initialize these values to 0 to begin with. The other one I want is uint32t, and that's block count. And I'm going to initialize that to 0. I'm going to go back down, and just below my lseek now, I'm going to read these values from the file. So to do that, I'm going to use a different function. This is called read. I'm going to say read from the file descriptor, and I want to read it into inode count. And I want to read explicitly 4 bytes. So I can say 4 or size of uint32t, and I will get the same thing. So I want to read 4 bytes. The second argument that we pass to read is a buffer, but it's really unaddressed. It's a pointer that we're passing to it. And so I'm putting ampersand here to say, please write it into this location. Please write 4 bytes into this location. And then I'm gonna just print this out for now. Print f number of inodes %d new line inode count. I'll write that out, and I'm going to connect to aviary again. I'm going to make it unused variable. Okay. So I'm going to say, I know this is an unused variable. We're going to use it right away. And ext2inspect takes 1 argument, the volume that I want to inspect. The number of inodes is 32, which we knew already when we made the file system in the first place. But now we've actually taken that out of the superblock itself. I want to do the same thing here, read fd, and then I want to read block count. So the next 4 bytes is block count. Here, this time I'll use size of uint32t. When I'm writing this code, if I have a table that tells me it's 4 bytes, I'll just put the number 4 in there. I will just hard code the number 4 in there. I know it's 4 bytes, so I'm just going to put 4 in there. And then I'm going to print this out as well. Number of blocks. Make. Number of blocks is 64. Okay, awesome. This is what we were hoping to see. This is exactly what we were hoping to see. Doing this is going to get painfully tedious, just like using hexdump to find our way through the file system. An alternative way to do this would be to read an entire structure all in one go. So rather than reading these individual bytes and populating individual values one thing at a time, we can just read an entire structure into memory all in one big blob. So I'm going to go back up here, and I'm going to make one change to this. And I'll make this change to the Git repository. So if you pull it, you might have merge conflicts, but you should be able to merge your changes into this. I'm actually going to delete this line, and I'm going to put a (1) here. So this used to say pragma pack and then a 1 in parenthesis. Now it says pragma pack push, (1). This part is functionally important. You have to actually put this pack pragma around the structure that you want to read with the read system call. What this says is you should align all of the members inside of this to a 1 byte boundary. In 2280, you talked about memory alignment a little bit. So lots of no's and a little bit. Okay, that's fair enough. Memory alignment on systems is kind of like relative to the architecture that says you can load this size of a word. It's going to be like a 4 byte words or 8 byte words, something like that. Memory alignment is trying to make sure that your structures are packed into that so that they're optimally taking advantage of word loads from main memory. But because we're loading this from a file, and because I know what the structure of this file looks like, I don't want my compiler messing with this thing. I want it to leave it in exactly the order and size that I have put in this file right now. I don't want it to change. I know that the first 4 bytes of the superblock is the inode count. And then immediately following that, the next 4 bytes is the block count. I know that, and I've put that into this structure. To make sure that my compiler doesn't change it and reorder things, I have to put this pragma pack there to say, don't do anything to this. Just leave it in this structure. Then I'm skipping 48 bytes. This is not something I would normally do, but I just want to have an illustration here of there's 48 bytes after these 2 things that I don't care about right now, because what I really want to see is this magic number. And magic, remember, was located halfway down that table. It's 48 bytes into that table. And I want to print that magic number out without having to skip around here. So what I'm going to do is I'm going to go down to my main function, and I'm going to declare an instance of this structure. I'm going to delete this line on line 36 because we're currently using that block count variable. I'm going to say ext2 superblock super. And I'm going to assign to this the value of curly braces 0. This says initialize the entire content of this structure to 0. Everything is 0. So inode count, blocks count, all 48 bytes in this skip array, and magic are all zeros right now after I've initialized it this way. If I don't initialize it this way, the read might leave things in a state that are just stuff that happened to be there, and I just don't want that to happen. I really just don't want that to happen. Once I've initialized it to 0, I'm actually going to do two things here. I'm going to go and finish up this idea of using my structure. So I want to go back to the beginning of my file, fd. I want to go to location 1024. I want to go back to the start of the superblock. And then what I'm going to do is I want to read from the file descriptor into this thing that's called super. I just want you to read into that structure that's on my stack right now. And I want you to read size of ext superblock bytes. Once I've done that, I read the whole thing. I read it all in one go, as opposed to like specifying these individual things to read. It's all been loaded in one big go. So I'm going to copy these two lines, and I'm going to paste them here. And then I'm also going to add printf magic percent. I'm going to do 0x%x. I want to print this out as a hexadecimal value. The 0x that I'm putting in front of it is literally the character 0x just before the number that gets printed out, so that I know that this is a hex value. And then what I want to print out here is not inode count as a bare name, but I want to print out super dot and super dot and super magic. I'm going to make this. Oops. Inodes count and blocks count. I'm going to make this, and I'm going to run this again, ext2 inspect, ext2 volume. And so we get the same values for inodes, and we get the same value for blocks, but now we also get this magic number. And if you don't remember from last time, which would be super fair, let's go back here, and I'm going to click on magic here, and the magic number is EF53. Which is exactly what we're expecting to do. So when I'm inspecting this file system, this is one way that I can say that the file system is in a consistent state. This magic number is exactly where I expected it to be. So I would hard code this and say this is ext2 magic, and then compare the value that I've read to be the same thing as what I've got here. All right, I'm going to go back here, and I'm going to take one step back. And the way that I want to take a step back is I also want to show you how to move around the file based on a relative location. So the part specifically that I'm thinking about is when we were taking a look at this volume with hex dump, and I'll go back to C in just a second here. And when we were taking a look at the inode table itself at location 4000, once we're here, I don't really want to calculate the absolute offset of the next inode entry in my table. I don't always want to do that. I just want to go to the next one. So I want to go 100, I want to advance 128 bytes basically. One way would be to read 128 bytes. So read it into a buffer to advance 128 bytes to the next inode in the table. But the other way is I can go to this absolute location. I can seek to location 4000, which is my first block here, with exFAT. exFAT, remember, is I want to go from like 0 directly to this specific location. The other that we care about here is the seek_cur. This says, advance this many bytes from where you are right now. Don't read anything, just move ahead this far. So if I wanted to read the super block's magic value, and I'm going to do that now, I would say uint16t, I'm going to declare a new variable called magic, initialize it to 0. And what I know about after these two values have been read is that the magic number should be 48 bytes after these ones. So I'm going to say this, lseek fd 48 seek_cur. Just move 48 bytes further into the file. Just keep on trucking. Just move 48 bytes into the file, and then I'm going to read the next 16 bytes from this. Magic. And then it's 2 bytes that I want to read. This is 16 bits for that magic value, for that magic number. Now I'll copy this and I'll paste this down here. And I'll change this from super.magic to just magic. And I'm going to make this one last time. I'm going to run it one last time. And we found it. We got to the right spot. The takeaway here is I can use exFAT to get to well-known locations in the file. So I know where the inode table starts because it's the first block after the super block. If I want to get to inode number whatever, I don't need to calculate the full address of that inode number whatever. I can seek to the beginning of the inode table and then use seek_cur to just skip ahead to the next 128 bytes, the next 120 bytes, or whatever the size of my inode structure is, as opposed to having to calculate these absolute offsets. You absolutely could do the absolute offset thing every single time, but doing seek_cur, I personally find to be easier to move around in my file with this approach. I'm going to post this code up to the, I'll push it to the Git repository so that this Git repository will get updated so you can find the code that I've posted for this. But I may also post this just alongside the course notes for today's lecture. Does anyone have any questions about this? All right. My goal here is that at this point, you should be able to get file system documentation and a volume and move your way around using hexdump and then write a program to do something similar. That's effectively what I'm expecting you to be able to do after this point. We are almost out of time, but what I want to do very quickly is take a look at this document here. This is what we're going to spend our time on Wednesday's class doing, is taking a better look at this document. This describes the exFAT file system documentation. The structure of this document is very similar to what we have been looking at with the ext2 documentation, but it describes exFAT instead of ext2. I think that this documentation is very good. It is comprehensive. The FAT documentation, FAT32 documentation, for context about why I think this is very good, the FAT documentation was like this PDF that you had to steal online. And then when you read it, it's like talking down to you. Like, you should know this and it's obvious that. I didn't really like it. I think that this is a much better document that describes in comprehensive detail about the exFAT file system. The main problem with it is that if I scroll down here, and I'm scrolling pretty quick, but if I scroll down here, outside of the occasional table, no pictures. There's no pictures in this documentation at all. There's none. It's all just text. And what I want to do is visualize this structure for you. And really, really specifically, my goal is to visualize how the FAT works, how this file allocation table structure works. So at this point, you should be able to describe how a specific file system is implemented. And you should be able to show how some common file operations, notably reading a file, we have read a file, that's what we did today, reading a file, are performed in terms of referring to a file system's data structures. And you should be able to do this with ext2 specifically. That's it for today. I hope you all have a great day. Stay warm, and I will see you all on Wednesday. Bye, everyone.